Using a Wye-Wye grounded transformer with an ungrounded primary has several downsides. Firstly, there is a safety hazard. Without grounding the primary, the system cannot clear ground faults safely. This can lead to dangerous overvoltages and electrical fires. Secondly, there is voltage instability. The grounding of the secondary neutral creates a low impedance path for current to flow during unbalanced loads. This can result in voltage fluctuations and imbalances in the 120 volts loads. Thirdly, overloading can occur. Due to the lack of a grounded neutral in the primary, the transformer may be overloaded when single-phase loads are applied. Fourthly, insulation stress can occur. The ungrounded primary can cause insulation stress on the transformer windings, potentially leading to insulation failure. Fifthly, there are reliability issues. Improper grounding can compromise the overall reliability and life expectancy of the transformer. Sixthly, there are code violations. Using a transformer in accordance with the manufacturer's instructions is required by code. This installation violates various electrical codes, including the National Electrical Code. Additional concerns include a lack of neutral. The absence of a neutral wire in the primary prevents the distribution panel from providing a grounded reference for single-phase loads. There are also compatibility issues. The Wye-Wye transformer configuration is not suitable for supplying both three-phase and single-phase loads effectively. This can result in unbalanced loads and poor power quality. It is strongly recommended that this improper installation be rectified by replacing the transformer with a Delta-Wye grounded unit and grounding the primary neutral. This will ensure proper operation, safety, and code compliance. Let's delve into each of these downsides in more detail. Regarding the safety hazard, a properly grounded system provides a low impedance path for fault current to return to the source. This allows protective devices, such as circuit breakers, to quickly detect and interrupt the fault, minimizing the risk of electric shock and fire. Without a grounded primary, a ground fault can cause the voltage on the ungrounded conductors to rise to dangerous levels. This is because the fault current has no easy path to return to the source, and the voltage will continue to rise until it finds a path, which could be through a person or equipment. The voltage instability issue arises because unbalanced loads on the secondary side of the transformer will cause current to flow in the neutral conductor. If the primary neutral is not grounded, this current will not have a return path, and the voltage on the secondary side will become unbalanced. This can cause problems with sensitive electronic equipment that requires a stable voltage supply. For example, a 120 volts load connected to a phase with a higher voltage will draw more current and may overheat. Conversely, a 120 volts load connected to a phase with a lower voltage will not operate properly. Overloading occurs because the transformer is not designed to handle unbalanced loads without a grounded primary neutral. When single-phase loads are applied, the current in the primary windings will become unbalanced, which can lead to overheating and premature failure of the transformer. The insulation stress issue is related to the voltage instability issue. When the voltage in the primary windings becomes unbalanced, the insulation between the windings can be stressed, which can lead to insulation failure. This can cause the transformer to short circuit, which can be a fire hazard. The reliability issues are a result of all of the above problems. The safety hazard, voltage instability, overloading, and insulation stress can all contribute to premature failure of the transformer. The code violations are a serious concern because they can result in fines and other penalties. The National Electrical Code requires that transformers be installed in accordance with the manufacturer's instructions. The lack of a neutral in the primary prevents the distribution panel from providing a grounded reference for single-phase loads. This can cause problems with sensitive electronic equipment that requires a grounded reference. The compatibility issues are related to the fact that Wye-Wye transformers are not designed to supply both three-phase and single-phase loads effectively. When single-phase loads are applied, the current in the primary windings will become unbalanced, which can lead to overheating and premature failure of the transformer. In summary, using a Wye-Wye grounded transformer with an ungrounded primary is a bad idea. It can lead to safety hazards, voltage instability, overloading, insulation stress, reliability issues, code violations, a lack of neutral, and compatibility issues. It is strongly recommended that this improper installation be rectified by replacing the transformer with a Delta-Wye grounded unit and grounding the primary neutral. This will ensure proper operation, safety, and code compliance. To further clarify, let's consider specific examples of how these issues can manifest in a real-world scenario. Imagine a commercial building with a Wye-Wye transformer powering its lighting and receptacle circuits. Without a grounded primary, a ground fault on a lighting fixture could cause the voltage on the other lighting circuits to rise significantly. This could damage sensitive electronic equipment plugged into those circuits, such as computers or cash registers. Furthermore, if someone were to come into contact with the faulty lighting fixture, they could receive a severe electric shock. Regarding voltage instability, consider a scenario where a large motor starts up on one of the phases of the secondary side. This sudden increase in current draw could cause a voltage dip on that phase, affecting the performance of other equipment connected to the same phase. For example, the lights might flicker, or a computer might malfunction. In terms of overloading, imagine a situation where a significant portion of the single-phase loads are concentrated on only one or two of the phases of the secondary side. This could cause the transformer to overheat, potentially leading to a fire. The insulation stress issue can be particularly insidious, as it may not be immediately apparent. Over time, the repeated voltage imbalances can gradually weaken the insulation within the transformer, eventually leading to a catastrophic failure. This could result in a complete power outage and significant damage to the transformer itself. The lack of a neutral in the primary can also create problems for sensitive electronic equipment. Many electronic devices rely on a stable ground reference to function properly. Without a grounded primary, the ground reference on the secondary side may be unstable, leading to malfunctions or even damage to the equipment. The compatibility issues can manifest in various ways depending on the specific loads connected to the transformer. For example, if the three-phase loads are significantly larger than the single-phase loads, the transformer may be forced to operate outside of its optimal range, leading to reduced efficiency and increased wear and tear. To elaborate on the code violations, the National Electrical Code, or NEC, provides specific requirements for grounding transformers. These requirements are designed to ensure the safety of personnel and equipment. Failure to comply with these requirements can result in fines, legal action, and even criminal charges in some cases. The specific NEC articles that may be violated in this scenario include those related to grounding and bonding, transformer installation, and overcurrent protection. It's important to consult the latest edition of the NEC for the most up-to-date requirement. When selecting a transformer for a specific application, it's crucial to consider the types of loads that will be connected to it. A Delta-Wye transformer is generally the preferred choice for applications where both three-phase and single-phase loads are present. This is because the Delta-Wye configuration provides a stable neutral point on the secondary side, which is essential for supplying single-phase loads effectively. In addition, the Delta-Wye configuration helps to isolate the secondary side from voltage disturbances on the primary side. The grounding of the primary neutral is also essential for safety. It provides a low impedance path for fault current to return to the source, allowing protective devices to quickly clear ground faults. Without a grounded primary neutral, ground faults can persist for extended periods, creating a significant safety hazard. It is important to consult with a qualified electrical engineer or contractor to determine the appropriate transformer configuration and grounding scheme for a specific application. They can assess the specific loads, voltage levels, and other factors to ensure that the installation is safe, reliable, and code compliant. Furthermore, regular inspections and maintenance are crucial for ensuring the continued safe and reliable operation of the transformer. These inspections should include visual checks for signs of damage or overheating, as well as electrical tests to verify the integrity of the insulation and grounding system. Any problems that are identified should be addressed promptly to prevent them from escalating into more serious issues. In addition to the technical considerations, it's also important to consider the economic implications of using an improperly installed transformer. The cost of replacing a damaged transformer can be significant, and the downtime associated with a power outage can be even more costly. Furthermore, the potential liability associated with a safety hazard can be substantial. Therefore, it's always best to invest in a proper transformer installation and grounding scheme to avoid these potential costs. To further emphasize the importance of proper grounding, consider the analogy of a lightning rod. A lightning rod is designed to provide a safe path for lightning current to flow to ground, protecting the building from damage. Similarly, a properly grounded electrical system provides a safe path for fault current to flow to ground, protecting personnel and equipment from electrical hazards. Without a lightning rod, a lightning strike could cause significant damage to the building and its contents. Similarly, without a properly grounded electrical system, a ground fault could cause significant damage to equipment and pose a serious safety risk to personnel. The grounding system is an essential component of any electrical system, and it should never be compromised. The consequences of improper grounding can be severe, ranging from minor equipment malfunctions to serious electrical shocks and fires. Therefore, it's crucial to ensure that all electrical systems are properly grounded in accordance with the applicable codes and standards. When troubleshooting electrical problems, it's important to always check the grounding system first. A faulty grounding system can cause a wide range of symptoms, including voltage fluctuations, equipment malfunctions, and electrical shocks. By addressing any grounding problems, you can often resolve these symptoms and prevent more serious problems from developing. The grounding system is often overlooked, but it's one of the most important components of any electrical system. By understanding the principles of grounding and following the applicable codes and standards, you can ensure the safety and reliability of your electrical systems. Remember, electricity is a powerful force, and it should always be treated with respect. By taking the necessary precautions, you can protect yourself and others from electrical hazards. The information provided is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical engineer or contractor before performing any electrical work.